All right, let's talk about the super materials that build our future, advanced composites. You know, the crazy strong, feather-light stuff in jet engines, F1 cars, you name it. But here's the thing. There's a huge problem. You can have a part that looks completely flawless, perfect to the naked eye, and it can just break, catastrophically. So what on earth is going on?
Well, the answer is hiding in plain sight, or maybe not so plain. The biggest threat to these parts is something you can't see, you can't feel, something that no standard inspection is ever going to pick up. It's an invisible enemy, born right inside the manufacturing process itself.
And this really shows you the two sides of the coin. On the left, that's the dream, right? That perfect, beautiful carbon fiber weave. But on the right, that's the nightmare. That's what happens when things go wrong. Tiny, microscopic cracks buried deep inside the material. This is the real battle in high-tech manufacturing, perfection versus reality. So, to get to the bottom of this, we're going to play detective. First, we'll identify this invisible flaw. Then we'll track it back to its source. We'll look at the damage it does, and then, this is the cool part, we'll see the technology that can actually predict it, and finally, how we can stop it. Let's get into it.
So, part 1, the invisible flaw. Here's a tough pill to swallow for any engineer. When you're making composites, defects aren't just a possibility, they're pretty much unavoidable. The real trick isn't just trying to make a perfect part. It's about understanding and controlling the imperfections that are bound to happen.
Okay, so here's our main bad guy. It's called residual stress. And the best way to think about it is like locked-in energy. It's a hidden force that gets trapped inside the material during manufacturing. Imagine these tiny forces constantly at war with each other, pulling and pushing from the inside. Over time, that hidden battle can make the part twist, crack, or just plain fail. Which brings us to our next clue. Where does this stress even come from? Well, it's born during the most important part of the whole process, the curing cycle. This is basically the high-stakes cooking recipe, where you bake raw materials under a ton of heat and pressure to make them solid. And this is what that recipe looks like. It's super precise. The red line is your temperature, and the black line is pressure. You see how they ramp everything up, hold it steady for a while to let the chemistry do its thing, and then cool it all back down. This isn't just throwing something in an oven. It's a carefully choreographed dance of physics and chemistry that takes hours. Now, here's the catch. As that part cools down and the resin gets hard, not everything shrinks at the same speed. The carbon fibers are different from the resin, and layers going in different directions shrink differently. That mismatch is exactly what locks those stresses into place, creating our hidden enemy. So what happens when that locked-in stress just gets to be too much? Well, you get a whole most wanted list of manufacturing defects, any one of which can ruin an expensive, critical part.
Now, they've got some fancy names, but the ideas are simple. You've got shape distortion, where the part literally warps. Delamination, where the layers peel apart like an onion. Matrix cracking, those internal fractures we saw before. And even tiny little air bubbles, or voids that create weak spots.
This is a perfect example of what can go wrong. This Z-shaped part was made on a mold that was a perfect 90 degrees. But once it cooled down, those locked-in stresses were released, and bam! The angle's bent inwards. It's not the right shape anymore. For a part on an airplane, that's a disaster.
And if we zoom way in, you see those matrix cracks again. And honestly, these are even scarier. Why? Because you might not even see them from the outside. They're like a ticking time bomb, a fundamental weakness that can grow and spread until the part fails unexpectedly down the road.
Okay, so we've identified the enemy. We know the damage it can cause. But here's where things get really cool. In modern manufacturing, we now have a secret weapon to fight back: advanced simulation. It's all about making that invisible enemy visible.
I mean, that's really the core problem engineers have been wrestling with, right? If your biggest threat is something you can't even see, how in the world do you stop it?
The answer is, you don't fight it in the real world. You fight it in the virtual world first. Using something called virtual manufacturing, engineers build a digital twin, an exact computer replica of the part. Then, they can run the entire curing process on the computer, watching exactly where and how those nasty stresses are going to build up.
And if you're wondering, does this stuff actually work? Just look at this. On the left, that's a real crack from a real-life lab test. And on the right, that's what the computer simulation predicted would happen. They are practically identical. The computer model literally saw the future. It's incredible.
The tech that makes this possible is a really clever model that basically works in two parts. One part simulates all the chemistry and the heat transfer of the curing process. The other part then takes that data and predicts the physical damage, the cracks, and it just nails it every time.
So let's talk about the payoff. This isn't just some cool science experiment. This predictive power is revolutionizing how parts are actually made on the factory floor, leading to smarter and way faster curing.
See, for decades, manufacturers used these super slow, super safe, one-size-fits-all curing recipes just to be careful. But now, with simulation, they can create a totally custom, optimized recipe for every single part. It's like having a master chef design the perfect cooking instructions for your specific dish.
And get this, the results are absolutely mind-blowing. In one study, engineers used one of these optimized cycles, and they slashed the curing time by 72%. 72. That's not just a small improvement. That is a complete game changer for how fast you can make these things.
When you add it all up, the benefits are huge. Production gets way faster, which is critical. The parts are stronger and way more reliable because you've designed out the risk of defects. And you're using less energy and fewer resources. It's a win-win-win.
So that leaves us with a really exciting question. Now that we have the power to see and defeat these invisible flaws before a part is even made, are we stepping into a brand new era of manufacturing? An era where we can design not just the perfect part, but the perfect process too? Getting us closer than we've ever been to the ultimate goal of zero defects? I think we might be.